Colligative properties are properties of a solvent that are affected by the presence of the solute. Okay, so these properties are going to depend on the concentration of the particles, not on the nature of the solute. Okay, so that's a key thing to remember, that really the way that these concentrations of the solute change these particular properties is just based on the number of particles. It isn't based on the actual nature of the solute. Okay, so here's some examples of properties that would not be affected by the concentration of our solute. We're going to just look at two of the properties that are. One is freezing point depression. When I dissolve a solute into a solvent, the freezing point of the solvent is lowered. Boiling point elevation. When I dissolve a solute into a solvent, the boiling point is raised. Okay, just kind of a basic reason behind this. Vapor pressure of a solution. This is if I have the solution in a closed container, okay, or the solvent by itself in a closed container, and I let it sit for a while, and then I measured the pressure due to the solvent evaporating. Okay, anytime we have a liquid with its surface exposed, we're going to have evaporation occurring. Okay, and in the same way, we got an equilibrium where we were like dissolving a solute and we got a saturated solution. We had an equilibrium between the dissolving process and the recrystallization. Here, if we put a liquid like water into a closed container, what's going to happen is it's going to start evaporating, and then the random motion of the vapor particles, they'll hit the surface of the water, and some of them will condense back. And so we have competing processes, and if you let it sit long enough, the rates at which that's occurring will be equal, and the pressure above the solution at the point where we have that equilibrium established, that's what we call the vapor pressure. And this vapor pressure is affects the things like freezing and boiling. Okay, so we're going to look at what happens when I have a pure solvent and then I add a solute to it. And one of the things that happens is that the vapor pressure is lowered. So let's look at a phase diagram here to see exactly what that means and how that affects the freezing and boiling points. Okay, so here we're showing our vapor pressure. This is our liquid. Let me get the pen out here. Okay, this right here, the red line, that's our, remember, this is our liquid vapor line. So here we have going this way across the line, I am vaporizing. Going this way across the line, I'm condensing. And so if I'm on the line, both processes can occur at that. Okay, so here if we see right here, if adding the solute lowers it, so this blue one, this would be for like pure solvent. So say pure water is this blue line. Okay, and then if we add a solute to it and make a solution, the vapor pressure is lowered. So that's our red line. And what you'll see is when I shift that, when I lower the vapor pressure, okay, if here, right here, remember 1 atmosphere is our normal boiling and freezing points. Okay, so right there. So look at what happens if we move or lower that vapor pressure line here and here. Okay, see how now the boiling point has gone up from what it was of the pure solvent, and the freezing point has dropped. Okay, so what we're going to do is we're going to look at how do we quantify that change. And this is a change that actually is very important. This is why we salt roads, for example. Okay, we add a salt to roads because basically adding that solute will lower the freezing point. So it means it can get colder without the water or melted snow freezing on the surface of the road. Okay, so here are the two expressions that we're going to use. All right, and this is just a table that has some examples of particular solvents, and then it has their normal freezing and boiling points, and then it has this constant. So the thing I want you to realize here is that these freezing point and boiling point constants that you're going to use in these two equations are specific to the solvent. Okay, remember we said colligative properties, the depression of the freezing point and the elevation of the boiling point don't depend on the type of solute we have, but the amount that it's going to change does depend on the nature of the solvent. So each solvent will have its own freezing point constant and boiling point constant. So let's just look at a couple examples. There's only two basic types of problems that I'll be asking you in this unit. So one like this, where essentially I want to know if I make this solution, what's my new boiling point or freezing point going to be. So this one's asking about the boiling point, but the process is exactly the same if you're using the freezing point. So here it says I have this non-volatile liquid soluble in water, and solution is made by dissolving 46 grams of my glycerol. So let's take a look first. Again, we know we're going to need moles. So let's go ahead and get that into moles. So that's going to be, oh, it has 92 grams in 1 mole. So I have 0.5 moles of my glycerol, and it says it's dissolved in 250 grams of water. So my molality of this is going to be 0.5 moles. 250 grams is 0.25 kilograms. So my molality is going to be 2. Okay, so my delta T for boiling is molality times my boiling point constant, and for water it's given as 0.512. So 2 times 0.512 is 1.024. Okay, my normal boiling point for water, it's 100 degrees Celsius. So my new boiling point, the boiling point goes up, is going to be 100 plus 1.024, or 101.024 degrees Celsius. Okay, so for the boiling point, you're going to add the change, add the delta T. For the freezing point, you would subtract it from the freezing point of the pure solvent. Whoops, wrong way. There we go. Okay, and here is one. This is how we can use this to actually identify an unknown substance, or to give us a piece of information to help us identify an unknown substance. So here it's telling me I have 14 grams of something, some unknown, and it's in 1 kilogram of benzene. That's my solvent is benzene, and I have 1 kilogram of that. And so it said its new boiling point with that dissolved in it is 81.7. We'll just pull out this information. And the normal boiling point of benzene is 80.1. Okay, this would be given to you, or you could go and find a table that had that in there. So it wants to know what the formula weight of the unknown is. Okay, so anytime it asks for this, we know you want to think about what units I'm dealing with. Grams per mole. All right, I have the grams of the unknown, so I know the first part of this. So what I want to focus on is, how do I find how many moles that is? Well, the data I have is talking about a change in the boiling point. All right, and I know that it's equal to this expression. So let's see what we have. All right, my change in the boiling point is the difference between the new boiling point and the original one for the pure solvent. Okay, I don't know my molality, but I do know my constant, which is 2.53. All right, so let's see. So I can find my molality. It's going to be, let's see, 81.7 minus 80.1. That gives me a delta T of 1.6. So we'll just do this in steps here. Okay, so my molality then is going to be 1.6 over 2.53. Whoops. Or 0.6632. That's my molality. Well, alright, so what am I going to do with that? I still need moles of that solute. Well, what is molality equal to? Moles of my solute over kilograms of the solvent. Okay, so I know my molality, and I don't know my moles, but I do know that we dissolved it in 1 kilogram of the benzene. So 0.632 moles is how many I have. So my molecular weight then is going to be equal to the grams, 14 grams that I had, divided by the number of moles, which I figured out from the change in the boiling point. So 14 divided by 0.632. So my unknown has a mass of 22.2 grams per mole. And so I could use this information along with other things that I might test about the unknown to identify it.